All right, hey guys, let's go ahead and get into 2.1 and 2.2 arithmetic and geometric sequences. Let's see what we can find out of what an arithmetic sequence is. Number one says find the next two terms, the nth term and the 100th term of the following sequences. So let's see here. Let's observe the sequence of numbers from 14, 17, 20, 23. I noticed that for each part of the sequence from one number to the next, I'm just simply adding 3 each time. So that lets me make a pretty decent prediction of what the next two terms are. I should get 26 and then 29. But then let's start to think about what determines the nth term. We can write an equation that describes the nth term. I know for a fact I'm adding 3 each time, but 3, well, how many times, right? If I'm on some term here, like if I have 4 digits here in my sequence and I want to somehow get to the fifth term, then I should be adding 3 a total of 5 times, right? And so we'll say 3 times n to dictate how many times I would have to multiply 3 by to get to that specific nth term. So if for some reason I was on the 10th term, I'll say 3 times 10, but there's some more things that would have to affect this equation. So how we can find the other parts of this equation is by just assuming or using what we already know. So for example, why don't I just do the first term? 3 times 1 should equals to, whoa buddy, should be equals to 14, right? That's my first term. Well, 3 times 1 is not enough to equals 14. To make this math statement actually true, I would have to include plus 11 here. So that kind of lets me um, create an equation that picks out any particular number within the sequence. So 3n plus 11. And you can see that this statement holds true for the rest of the sequence of what we know so far. Let's say supposedly I want the second part of my sequence. Well, I'll take 3 times 2 plus 11. And hope to God I get, what is it, 17? And it seems like I do get 17. So it does hold true for all parts of my sequence. Now that I've designed an equation to describe any nth term, I can use this to find the 100th term of the sequence. So I have 3 times 100 plus 11, which is equals to 311. Alrighty, now let's move on to part B, where we try to do the same thing again. So let's try to predict what the next two terms are. As I look at the current sequence, these first 4 terms, I see that I'm subtracting by 7 each time. Since I can assume that, I can assume that the next term will be 30, oops, not 31, I will say 29, and then 22. And so let's come up with an equation that determines any given term, right? So it could be the nth term, right? It could be 5, 7, 10, doesn't matter. So let's write an equation, and based on my previous work, I'm going to use the difference from each term as my starting point of my equation. So I'll say negative 7 times 10. And then to predict the rest of the equation, I might try to set this up where it's all equals to one of the terms that's already given. Let's pick the first. So I'll say it's all equals to 57. Well, what missing component will make this statement true? Well, I might say, actually let's plug in 1 into n so far. So I know it's negative 7 times 1. And to make it equals to 57, well, it would have to be equals to 64. So I would say plus 64 here. So now that I've designed an equation that describes any m term, I could plug in 100 now to find the 100th term. So I'll say negative 7 times 100 plus 64. And this should be equals to negative 620, ooh, not 20, 636. Alrighty, let's continue. Now let's do the last one. Pause the video now if you want to try it on your own. If not, just follow along. So same thing again. Let's go ahead and find the difference between each of my terms here of my sequence. So it seems like I'm adding 14 each time. So if I had to predict the next two terms, it would be 38 and then 52. Now let's write an equation that describes any given n term. So I'll use the difference that was provided, 14 times n Then let's complete this equation by setting it equals to a particular term of my sequence. Let's just pick a random one this time, not the first one. Let's pick the third one to show that that would still work. So 14n plus or minus what will give me 10. So since that's the third term, that means I'm plugging in 3 for n this time. Plugging in 3. So 14 times 3, I believe is, what is that, 28? 32, 42? 42 plus what will give me 10? Well, that seems like it would be, well, I can't do that in my head. Um, why don't we just subtract 42? Well, it's negative 32, right? So that'll be 42 plus, or sorry, minus 32 equals to 10. So I was able to figure out the exact formula here. And you can see that this kind of holds true for any given number in the sequence. So if you don't believe the number, I might try it out myself just to make sure that I did it correctly. Let's say I want the first term. I'll take 14. Where's my calculator? 14 times 1 minus 32. And hopefully I get negative 18. Hopefully I get negative 18. And I do. So everything seems to be working out as planned. So if I want the 100th term, 14 times 100 minus 32. Was that 1400 minus 32 is equals to, mental math, don't fail me now, it's 13, what is that, 68, 1368. Alright, there's the first part. I'm going to do a quick pause here to blow my nose, and I'll be right back. Alrighty, let's continue. Let's do number 2. Write the first 4 terms of the following sequences. Well, if I observe the sequence, this is what you call a recursive sequence. The reason why it's called a recursive sequence because we are provided one of the parts of our sequence, usually the first term. And if we want to figure out any given term in the sequence, so a sub n, I would always have to use the previous term to help me find that. So that's why it's called recursive. So let's see what we can do to find the first 4 terms of the following sequences. So here, I know what a sub 1 is. That's equals to 6. But let's kind of do it mathematically here. Let's actually just say a sub 1 is equals to 6. Let's just restate what's provided. If I want to find a sub 2, that's equals to a sub 2 minus 1 plus 2, which is equals to a sub 1 plus 2. And I know what a sub 1 is. A sub 1 was already provided to us, right? That was 6. So 6 plus 2, which is all equals to 8. So that's a straight up mathematical way to kind of do this. Or if you kind of want to think about it in your head, hey, I'm just taking the previous term and adding 2 to it. So if I wanted to figure out what a sub 3 is, and if you want to show in the math, that's totally fine. Here, I'll just say, oh, let me reference my previous term and add 2. Well, there's my previous term. Let's add to it, and I get 10. And I'm just going to repeat that process for my 4th term. A sub 4 is equal to my previous term, where I add 2 to it, so 12. So there's the first problem, or first part of this problem. All right, now let's do the second part of this problem. This equation is specifically in explicit form. Right? It's not using any particular um, prior numbers of the sequence, just what is this number of that you desire, and just plug in what you want, right? It's explicit. So let's just plug in a few until we have 4 total terms. So we'll plug in 1 first. If I plug in 1, I get negative 7 times 1 plus 2, which is equals to negative 5. Let's do b sub 2. B sub 2 is equals to negative 7 times 2 plus 2, which is equals to negative 12. Let's do b sub 3. That's equals to negative 7 times 3 plus 2. That's equals to negative 19. If you don't understand the math, you can already tell the pattern for each values that the difference between them should be by negative 7. So if I want to predict the last one, just subtract 7 from the previous term, and I should get negative 26. Alright, let's move on to the third and fourth. However, they are exactly just like parts 1 and 2 here, so I'll leave them up to you for practice. Right. Before we continue, it might be useful to know some equations here. Let's go to the bottom here and kind of summarize what we've been able to kind of already see. An arithmetic sequence is a sequence with a common difference. What they're describing here is what we notice happened from each number of the sequence, right? For example, the first one here, right, we were adding 3 each time. Second one, subtracted 7. And third one, we added 14. So there's our difference amongst each numbers of the sequences. That's what they're describing in this statement. And then we proved a sequence is arithmetic by showing this statement. We showed that a sub n is equals to a sub n minus 1 is plus whatever difference. Meaning I can take any given position on the sequence as long as I use the prior number, as long as I use the prior number and add the difference, I should be able to get the number that I so desire. So as long as that occurs for every single number of the sequence, then it should hold true, right? So as we kind of observe all these numbers here, that if I pick any particular number within the sequence, let's not say the first one, it will always rely on the previous one where I added 3 to get it, right? So if I somehow want to get 20, I took the previous one, added 3. So there's always a common difference amongst all the given um, numbers of my sequence. All right, so now let's continue with the rest. Let's take a moment and write some of the general forms. We've already saw the recursive one. Let's rewrite it again. Typically, it will always be where they give you one of your uh, numbers of your sequence. So we'll say a sub 1 is equals to a sub 1, right? Where, of course, this particular number here is given to you. Followed up by the instructions of your sequence, right? So they might give you one of the terms, and then it'll tell you exactly how to find the rest of the terms. So a sub n is equals to a sub n minus 1 plus d. Oh, you're on my caps key, bro. Let me move you a little bit, sorry. All right. Now let's talk about the explicit form. Now, oh, he's so cute. There's there's 3 various forms that we can write this in. One that we saw earlier. However, let's kind of be more specific now. Let's say I had a sub n is equals to a sub 1 plus n minus 1 times d. Right? This is probably the main one that we're going to be using, but we might use some various others. All right, this is definitely one of the main ones. Another one that's nice, however, I don't use this as often, but it's still usable, is a sub 0. A sub n can be equals to your, um, technically not your first term, but the term that precedes the first term, will be n minus 0 times d. But technically, I don't really need the n minus 0 part. It's just for me to show you how I derived it from this original one to get to here. So let's erase the minus 0. Typically, you just see it like this. And then the third one, I would say, is the second most important out of all this. But to derive it, it's based on this previous knowledge, is that I can predict any given number of a sequence as long as I have a prior number of the sequence. So the most prior that you can think about is a sub 0. But what if I want to do any given prior number of the sequence as long as it's before a sub n? So I would claim that a sub n is equals to a sub k plus n minus k times d, where n is greater than k. Right? I'm referencing a specific point of my sequence, one specific number, but I would have to use some previous number of the sequence. Doesn't have to be the first one, doesn't have to be the 0th one, but it has to be somewhere before. So this is a good general form to use if they just give you any particular two, because sometimes they won't give you a sub 0. So I'd say priority to think about what equations to quote unquote remember is this one and this one, right? Alrighty. I'm going to actually write good mathematical notation here. I'll say where n is greater than k. Alright, let's continue. Let's scroll back up. And actually, I might duplicate these equations in case I want to reference them as I go through these problems. So let's duplicate, bring them up to where we were just at, and continue. to see if we can use these to help us out. So this one says, number 3, given two terms of an arithmetic sequence, find the nth term. So to think about what we're given. You have never approached these problems before, so I'm going to try to give you the context. It's kind of just, I find it like kind of like a puzzle piece. I want to see which one of these equations do I have the most puzzle pieces for, fit them in, and find the missing puzzle piece to continue to produce more good work, right? So we just want to make sure each mathematical statement is true one right after the other. So let's see what I do now. They provided to us two particular numbers in the sequence, the fifth number of the sequence, as well as the 11th number of the sequence. So that's not helpful for us in the first equation so far, right? This demands that I have some random number, which I guess I do, but also requires the first number of the sequence. I don't have that, so not usable, this one. Nor is the second one useful because I don't have the quote-unquote 0th term of the sequence. But I can use this one, right? I can use a sub n is equals to a sub k. The requirement here is that, well, n is greater than k. As long as I have some number in the sequence that's bigger, or not bigger, I would say later in the sequence as the first one, right? So this is definitely true, right? I have the fifth one and the 11th one. So let's plug in what I know into the third equation. So I'll say a sub 11 is equals to a sub 5 plus n minus k, where n is 11 and k is 5, all times d, right? I know every single piece of information here except for d, which then infers that I can solve for d now. So let's go ahead and simplify and solve for d. I know what a sub 11 is. I'll plug that in to be 35. I also know what a sub 5 is. We plug in 11. Now rewrite everything else. Well, we might as well simplify that. That's just going to be 6 times d. And if I solve this, I get 24 is equals to 60. Divide by 6 to solve for d, I get 4 is equals to d. Now that I know what d is, I have three things I now claim to know. I know this, this, and this. And now that I do know that, that lets me probably use one of these equations now to solve for a sub 1. You can also solve for a sub 0, but again, I kind of lean towards that one, just because I prefer the quote-unquote first term. So let's do that. So a sub n, again, being any point that we already have known. So I would either pick one of these two here. Does not matter which one. I'll just pick the first one. So let's plug in what I have now. A sub 5 is equals to a sub 1. That's something I can solve for now. Times 5 minus 1 times d. Let's simplify this and solve for a sub 1. So I get 11 is equals to a sub 1 times 4 times 4. So 11 is equals to a sub 1. Oh, I should have a plus on here. Plus 16. Which thus means I have negative 5 is equals to a sub 1. So the first number of the sequence now, I claim to know to be equals to negative 5. Now I know that, I can re-plug that into the first equation and leave a sub n unplugged in for, because then this mathematical statement infers that I can now solve for any particular number of my sequence, as long as I write it out like this. So if I ever wanted the 100th term, the 30th term, or whatever term I want, this is the equation I would use, right? This is now in general, with not knowing what n is, what number of my sequence I want to be at. So I think we finished out the problem, right? I solved for find the nth term, right? This equation describes the nth term. All right, let's move on to part B now. All right, these steps will resemble just like the previous problem. So we just want to practice the kind of sequences of steps. Hope you like that joke. The sequences of steps in case on how to remember how to do it, right? So let's see. I'm given two arbitrary numbers of my sequences. So let's use the third equation first. So I'll have u sub 13 is equals to u sub 7 plus 13 minus 7 times d. Right, I know every single part of this so far except for d, so this helps me solve for it. So I get, what is it, negative 3 is equals to 27 plus, what is that? 6 times d. Subtracting 27, I get negative 30 is equals to 60. Divide by 6, I get negative 5 is equals to d. Now that I know what d is, let's go and plug this information in, or these three pieces. Or almost, I would say not all three, but I can now use a different equation, right? Let's use the first one, where a sub n is something that I already know, not just any arbitrary one. So I might pick u sub 13 this time. So I'll say u sub 13 is equals to a sub 1. Let's say, actually use the same letter. Let's do u sub 1 plus 13 minus 1 times d. But in case I know what d is, it's negative 5. So I know every single piece of this except for u sub 1, so we're solving for the first term now. So let's plug in what I know. I have negative 3 is equals to u sub 1 plus 12 times negative 5, which means I have negative 3 is equals to u sub 1 minus 60. Adding 60 to both sides, I now get 57 is equals to u sub 1. Now that I know the first term, I can just plug this back into the original equation. Don't plug anything for a sub n, so I can generalize it for any nth term. So a sub n now is equals to 57 plus n minus 1 times negative 5. There's my equation that describes the nth term. Alright, now let's move on to number 4. So again, we'll try to bring down those equations again in case they're useful. We'll duplicate them real quick, bring it down. So let's see which one we'll reference. So I know quite a lot of information here on this first part of the problem. I know what my first term is. I also know what my difference is. And I'm trying to look for, I guess, which term is equals to 101, right? I'm not sure which term this is. This could be the 7th, the 8th. I know it's not the first, but I'm trying to figure out which term 101 pops up. Okay, so with that being said, I think now that since I know what a sub 1 is, I think it's a good equation to probably plug into the first one, right? The first one looks pretty ideal. So let's see here. I have a sub n, 101 is all equals to, sorry, a sub n is equal to 101, all equals to 20.5 plus n minus 1 times d, which is 3.5. And then I'm just going to simplify this and solve for n. So I get 101. Let's just subtract 20.5 now. How about that? So it'll be, what was it, 80.5 equals to 3.5n minus 3.5. And then I would add 3.5 to both sides. This will give me 84 is equals to 3.5n. And then I'll divide by 3.5 and I'll get n is equals to, not sure what this is, but let's use our calculator. 84 divided by 3.5 was a 24. I think that's answered the problem, right? It identified the value of n, so I kind of plug this back into this if I want to. So I know that the 24th term is equals to 101. All right, let's move on to the next problem and see how it's different, right? I'm given three pieces where I'm not given a sub 1, which is unlucky, but I think it's fine. What I do know is two arbitrary numbers though, so I'm going to reference the previous work that I did. When I did know two arbitrary numbers of my sequence, I was able to solve for d as my initial step. So that's what I'm going to do here so I can get more info out of this problem. So this should feel very familiar. I have a sub 17 is equals to a sub 6 plus 17 minus 6 times d. So plug in what I know. We can try to simplify and solve for d. I get that negative 52 is equals to 47 plus 11 plus 11d. Subtract 47 from both sides. I get negative 99 is equals to 11d. Divide by 11, I get negative 9 is equals to d. Now that I know what D is, I could probably plug this back in to the original, like one of the equations, and solve for a sub 1, just like I did in this previous problem here. So let's see. All right, now let's just use any arbitrary point. Let's use a sub 6. 47 is equals to a sub 1 plus n minus, not n, we know what n is, it's 6. 6 minus 1 times negative 9. Let's simplify and solve for a sub 1 now. So I have 47 is equals to a sub 1 minus 45. Add 45 to both sides. And I should get 92 is equals to a sub 1. Now that I know what a sub 1 is, I can now try to solve for a sub n by using the first equation. So I get a sub n equals to a sub 1 plus n minus 1 times d, which was negative 9. Now let's simplify. Plug in what I know and simplify. I get negative 268 equals to 92 plus, not plus I guess, I'll say minus 9n plus 9. So we'll simplify here and solve for, sorry my headset died, but I'm back now. Alright, so now I just need to solve for n. So if I combine like terms and move them over, 92 plus 9 is 101. So I'll take negative 268, subtract 101, and I get negative 369 is equals to negative 9n. We'll divide by now negative 9. Oops, negative 369 divide by negative 9. So I get n is equals to 44. Which means that this particular term here equals to negative 268 is the 44th term. Alrighty, so we finished a good chunk of the problems. Only last problem here left is the um, fifth row problem here. So let's see what I get. Each row in Williams Theater has 6 seats more than the row in front. The first row has 18 seats. How many seats are in the 20th row? So there's quite a bit of info that I know now. I know for a fact that, well, the first row, let's label it A sub 1, the first number of my sequence, should be a total of 18 seats. I also know the difference, right? D should be equals to 6, right? Each following row is always 6 more than the previous one, where the first initial row here is 18 seats, right? And so we're trying to predict, well, what is the 20th row? A sub 20. But just plugging in what I know, I can claim that A sub 20 is equals to A sub 1 plus n, well not n, I know what n is, 20 minus 1 times d, which is equals to 6. So I'm currently just referencing the first equation that I have here. So plug in what I know. I don't know what a sub 20 is. That's what I'm trying to figure out. A sub 1 is 18 plus, I guess that's 19 times 6. And then I'll just plug that into my calculator to see what I get. Sorry if I sound so sickly and stuffed up. I can't help it. I went for a run and it screwed with my whole body. But I promise you I'm fine. I might not sound fine. Sorry, 18 plus 19 times 6. So I get that a sub 20 is equals to 132 seats. So we'll finally make a full claim. We'll say at the 20th row, there are 132 seats. Perfect. We finished the first part of this. Now let's move on. Now let's move on into what it means to be a geometric series. Alrighty, let's go ahead and finish up the rest of the geometric sequences. If there was an awkward cut, I am recording the next part the following day. I was feeling way too sick at that time. So hopefully I sound a little bit better. If not, sorry. Okay, so let's see. Now let's start working with geometric sequences. Here it says I want to find the next two terms, the nth term and the 10th term of the following sequences. So let's try to see the behavior of the sequences so far. It seems like from one number to the next, I'm multiplying by 2 each time. Knowing that, I could probably predict the next two terms by just multiplying by 2 again and again. So I get 48 and then 96. And then I want to somehow come up with an equation that describes any given nth term. Well, let's do some discovery here. Although I could try to probably say, hey, it's going to be 2 times some number because this will occur however many times depending on what number of the sequence I'm on. However, that might not be so easy to see. So instead, let's create a table. Let's say n and a sub n are the values I'm going to evaluate from my table. Let's do 1, 2, 3, and 4. This is going to reference the first 4 digits of our sequence, which was already given to us in the problem. So I'll say 3, 6, 12, and 24. And then I'm going to do an ellipsis here to infer that, hey, I'm skipping a whole bunch of numbers of this table to get to the quote-unquote nth digit, right? This could be anything. And I'm trying to find an equation that describes that nth digit. So let's see. Besides the classic of, yes, we're multiplying by 2, let's think about, well, how can I get the first time? Or sorry, the first number of the sequence. Do I also multiply by 2? How can I rewrite this where it is being multiplied by 2? Because that's how we get the rest of these numbers. So I might think, well, let's just say it. 3 times 2. How can I change this to make sure the statement is true? Well, if I introduce the exponent of being 0, that this is now true. Right? This is 3 times 2 to the power of 0. If I continue this line of logic for the rest of the terms of my table, I can claim that 6 is 3 times 2 to the power of 1. 12 is 3 times 2 to the power of 2. And then 24 is 3 times 2 to the power of 3. And so now I can see that this exponent is constantly changing, which more than likely means these exponents should be depicted by a variable, right? That's our dependent variable. Why is it changing? What is it dependent on? If I look at the n values and then try to associate them with my exponents that I currently have, you can see that they're simply just n minus 1 for that current column that I'm on. So with that being said, this lets me rewrite this question mark into a formula that describes any given nth term. It would be 3 times 2 to the power of n minus 1, dependent on where I am in the sequence. Just simply subtract by 1. So there's my equation, 3 times 2 to the n minus 1. One thing to make note of is that this looks very close or pretty much exactly like the format of a exponential function. F of x is equals to a times b to the power of x, right? When the variable is in the exponent. A being 3, b the base being 2 here. So it's very familiar to an exponential function. Now with that aside, let's think about what is the 10th term. Let's go ahead and plug in 10 and see what we get back in our calculator here. So let's see. 3 times 2 to the power of 10 minus 1, which is simply just 9. So I'll put that in. I get 1536. Let's repeat the same process again for part B. I notice the pattern here is that it seems like I'm dividing by 5 each time to get to one term to the next. But it may be better for us to think about it as multiplying. So we want to kind of stay in the same realm of an exponential function where you're multiplying by a certain number. So in this case, instead of saying dividing by 5, I'll say we're multiplying by 1/5 instead. Just so we can stay consistent with the previous rules where we're multiplying by 2. So we'll continue to multiply by 1/5 to the rest of the terms. The next number of my sequence should be 1. 1 times 1/5 is now 1/5. And let's try to determine a formula that describes the nth term. So based on our assumptions from the previous problem, it seems like this 3 came from the first initial number of our sequence. And then the 2 part came from what number I was multiplying from one number to the next in my sequence. Using that to infer the formula of this next sequence in part B, I could say that we should have 125, the first term, times the number I was multiplying each time to get one sequence to the next. So sorry, one number from the sequence to the next. So I'll say 1/5 inside the parentheses, all to the power of n minus 1. Now I can go ahead and plug in 10 into n and figure out what the 10th term is. Let's go ahead and put that into my calculator. 125, 1/5, the power of n minus 1. So 10 minus 1 is 9. So I get a really nasty scientific number here. However, as long as I convert it back into a fraction, it should give us something easily understandable. So this is all equals to 1 over 15,625. Now let's move on to the third problem. This one might not feel so easy to think about, seeing what we might multiply from this number to the next. It doesn't seem like it's just multiplied by 1/2 or 1/3. So thinking about it might not feel so easy. So if they're not as easily accessible as the previous two problems, then I would suggest that, hey, is there another way that we can think about what we're multiplying by? Let's go back to the previous problem and see how else we can find 1/5 if you didn't see it evidently, right? Is there a way that we can do it with certain precision, right? With certain steps? Well, one way to get 1/5 here out of the sequence is by taking any arbitrary number in my sequence. I'll pick the second one and divide by the previous number in my sequence. If I took 25 divided by 125, that does get me 1/5. So that's one way to get the number that you're multiplying from one number of your sequence to the next. I'm going to use that logic here to help me figure out what I'm multiplying by each time for this specific sequence. So I'll take negative 54 and divide by 81. Let's see what I get back in my calculator. Negative 54 divided by 81. I get 0.666667 repeating, I assume. But if I convert it to a decimal, or sorry, a fraction, I get negative 2/3. So I know I'm multiplying by negative 2/3 each time to get from one number to the next. If you don't believe me, try it out. You'll see that you'll get every single number if you start at 81. So let's start at negative 24 and multiply by negative 2/3. I get 16. Do it again. Oops, that doesn't seem right. Let's do 16 times negative 2/3. And I get this number, which I probably don't want to write down. Let's see what it looks like as a fraction. And I get 32 over 3, or perhaps a negative 32 over 3. So now that I figured out the next two terms, let's write an equation that finds us the nth term. So in this case, I'm going to use the first number of my sequence, as well as a ratio that I'm multiplying by each time, which is negative 2/3 to the power of n minus 1. Now let's plug in 10 for n and find the 10th term of the sequence. 81 times negative 2/3 to the power of 9. So I get a really weird decimal number. I probably wouldn't write that down. Let's see what it looks like as a fraction. See if it's nice, and it is pretty nice. Negative 5/12 over 243. Now, let's keep going. Before we kind of continue with these problems, or actually let's just do number 7, and then we'll go down to the bottom for our summary. So, write the first four terms of our following sequences. If you recall in our arithmetic sequence that this right here is in recursive form. Right? We know that because this statement here says that I can find any arbitrary number in my sequence as long as I use the previous number in the sequence and do something to it, right? That's pretty much how we know it's recursive here. So let's find the first four terms. A sub 1 is equals to 6. A sub 2 is equals to 2 times A sub 2 minus 1. And that's all equals to 2 times A sub 1, which of course is 2 times 6, which is equals to 12. So as long as I use the idea that, hey, I'm just multiplying by 2 to the previous term, it can be readily available to figure out what a sub 3 is without showing all this work. I know I'm just multiplying by 2 to the previous term. My previous term currently is 12, so 12 times 2 is 24. Do it one more time to get a sub 4, my fourth term. I get 48. We'll repeat the same process again by plugging the first four digits starting from 1 to get the first 4 terms here for the second equation. Recall that this is an explicit form. So I'll plug in b sub 1, so 1 this first time around. So 7 times 3 times 1 minus 1, that equals a 7 times 3 to the power of 0. Recall that anything to the power of 0 will just give you 1. So 7 times 1 is technically just 7. And we'll keep going. B sub 2, right? 7 times 3 to the power of 2 minus 1. That's equals to 7 times 3 to the power of 1, which is simply just 7 times 3. That gives me 21. So it seems like each time I do one of these, I'm just multiplying by 3 each time, which resembles the base of this current formula or equation. So I'll rewrite the next term just by thinking about multiplying by 3 to the previous term. So 21 times 3 is simply, what is that, 63? B sub 4, take my previous term here and multiply by 3, and I get 189. Now you can repeat those same exact steps again, just by plugging and chugging to find these two. But I'm going to skip them and leave them for you as practice if you'd like. Alright, now let's move on to number 8. Actually, before we do, let's talk about the formulas down below, and then we'll go back up there and see how we use them. So in summary, a geometric sequence is a sequence with a common ratio. The ratio that I'm describing is the numbers that we multiplied by each time to get from one number of the sequence to the next. So in the first one, we multiplied by 2. 2 is the ratio here. Part B, we had a ratio of 1/5 being multiplied each time. And then negative 2/3 for part C. All right, now let's continue. So we proved a sequence is geometric by showing the following. A sub n is divided by a sub n minus 1 is all equals to r. We've already kind of practiced this already inherently, in case you forgot. When we were struggling with part C here to figure out how to get the ratio, what we did was take a current term and divide it by the previous number to get the ratio. Right? We just proved that naturally. So we can just write that in as something we can assume as a definition, and then write some general forms here. Our recursive form will always start with a curly bracket where we're given the first term of our sequence. This here will just be always given to you. And then, of course, some arbitrary number of my sequence, if I want, will be equals to a sub n minus 1 times whatever ratio. So the previous term multiplied by whatever ratio that I have. Let's move on to the explicit form. Explicit form has 3 equations, very similar to the one that was arithmetic. There's one where you have an arbitrary number of the sequence, as well as the first number of the sequence, times r to the n minus 1. We also have a sub n is equals to a sub 0 times r to the n minus 0. And again, I'm only emphasizing the minus 0 part to show you that we derived it from the previous equation. I don't necessarily have to write it. And then we have one more. A sub n is equals to a sub k times r to the power of n, where k is less than n. What we're saying here is that a sub k is just some prior number of the sequence, not sure which one it is, that it could be anything prior in the sequence to our arbitrary number in the sequence. So it doesn't have to be a sub 0, it could be any of them. So we'll drag and drop this in case it's useful to us along the way as we go through these problems. So let's see. Let's go ahead and find what we're supposed to do here. What does it say? Given 2 terms of a geometric sequence, find the nth term. All right, let's see what we can use in terms of my equations and which ones will be useful. So I'm given 2 arbitrary numbers in my sequence, so more than likely I should probably use the third equation where it does involve 2 arbitrary numbers in a sequence, right? Very similar to the ones we did in arithmetic. So I'll plug in g sub 4 as our leading sequence, a number in the sequence. So I'll say 324. 324 is equals to 144 times r, which I don't know yet, to the power of, ooh, I forgot something in the equation. It should be n minus k here. I apologize. N minus k. So make sure you go back down there and write n minus k here as well. All right, we're good now. All right, and so my n in this case is 4, so I'll have 4 minus 2, and then we'll simplify this equation to solve for r. So let's divide both sides by 144. 324 divided by 144. That's 2.25, but let's see what it looks like as a fraction. Is it nice? And yes, it is nice. So I'll say 9 over 4 is equals to r to the power of 2. And to solve for r, I'll take the square root of both sides. And I get that, well, that would be a r is equals to plus or minus 3 halves. Recall that anytime you take the square root of a number, it's going to be 3 halves. Or sorry, it's going to be plus or minus that specific number. Now, let's go ahead and move on and proceed with the problem. Let's see what else I can find. Now that I have r, just like in arithmetic, I can now plug this back into the first equation and solve for the first number of my sequence. Using some arbitrary number that I already have, perhaps we'll pick this one, as our a sub n. So I'll say 324 is equals to a sub 1, which actually I shouldn't say a sub 1. Let's use correct notation that was already denoted to us. They were using g, so I'll say g sub 1 times r, which we just figured out. And we'll do the positive 3 halves this time. We'll see that the negative 3 halves is not all that different. So we'll have 3 halves to the power of 4 minus 1. Simplifying this, I get 324 is equals to g sub 1 times 3 halves to the power of 3. And I'll take 324 and divide by 3 halves to the power of 3. And that should be equal to g sub 1. So let's put this right here into the calculator. So I have 324 divided by a negative 3 halves to the power of 3. Or did I do? Oh, I didn't mean to say negative 3 halves. I apologize. Let's go back up and fix that. We're not doing that one yet. So I'll just say positive 3 halves. What do we get? We get positive 96. So g sub 1 is equals to 96. And now I'm going to rewrite the first equation, plugging in what the first number of my sequence. So I'll say a sub n now for any given number of my sequence that I want is equals to, it's not a sub n, let's do g sub n. G sub n is equals to 96 times r, which was 3 halves, to the power of n minus 1. So there's one equation that describes the nth term. Now let's go back and plug in negative 3 halves if it also does that for us. The math won't change up all that much. You see that technically this would become negative 3 halves. Then that would become negative 3 halves. Then over here, that would still be negative 3 halves. And if I was to put that in the calculator, which I did a moment ago by accident, I get 8g sub 1 is equals to negative 96. And I want to do the same thing to write my final answer. I'll say g sub n could also be equals to negative 96 times 3 halves, negative 3 halves, to the power of n minus 1. And these two equations might be valid solutions to finding the nth term. But when we find them, it's also a good thing to probably check whether or not these answers that we found actually work. Let's see if I was a, whoa, buddy, let's go put you right back down. Yeah, relax. All right. Um, so I would say here, let's go ahead and test out this equation to see if it produces the two given terms. If it doesn't, then they wouldn't be valid options. So what I would do first is do 96 times 3 halves to the power of, bro, you gotta chill. Chill. Maybe if I pet him, he'll stop jumping up there. So what was I saying? Oh yeah, 3 halves to the power of 1 minus 1, right? I'm plugging in 1 for n to find the first term. So if I plug in 1 here, 1 minus 1 is 0, so I'll just raise this to the power of 0 now in my calculator. So this should give me the first term, and it does. It gives me 96. So if I continue to multiply by 3 halves here to this term that I'm currently on, I should produce the next number of my sequence, which should be the second term. The second term was given, it should be 144. So hopefully when I multiply by 3 halves again, I get that number. It seems like I do. And I'll continue. If I click execute one more time, I'll multiply by 3 halves one more time to give me my third term. I don't have a third term, so I don't have to worry about that. I'm worried whether or not my fourth term is also true. Let's press it one more time, and I get that it's 324, which matches with the 324 I get here. So far, so good. So let's keep going. What if, I mean, now let's keep going. Let's box in the first one for sure. That one for sure works. What about the second one? So the only thing that really changes here is that I have negative 96 times a negative 3 halves to the power of 0 to start off with. Let's find the first term of this one. Notice here I get negative 96 for my first term. That's different from the positive 96 I got earlier. But that's not an issue because what we're given is this G2 and G sub 4. I'm not given the first one, right? It could be anything. So far I haven't redefined or this was it um, break the law so far in terms of what was given to me, right? Everything's okay. So let's multiply by 3 halves again and see if it produces a second term though. That's what we're kind of worried about. So let's multiply by negative 3 halves. So I get 144. So I was able to find the given information so far. Let's do it again to find the third term. And I don't have the third term here, so we're good even though it's some negative 216. And I have the fourth term, I do get my positive 324. So both of these equations are valid answers that produces the given terms of this geometric sequence. Although for sure, these are definitely different, right? This one produced 96, and then was it 144, then 216, and then 324, as I kept multiplying by 3 halves. The second equation, of course, did negative 96, then 144, negative 216, and then positive 324, right? Although they are definitely different by the signs for a few numbers of the sequence, it doesn't matter. I'm only worried about whether or not these were valid with what I was defining the problem. And they are, so both equations are fine. Alrighty, let's go ahead and move on to part B and see how this one is different. However, it's not really different at all. It's the exact same steps as this one, right? It's the exact same steps verbatim. But let's run through it in case you need the experience. So I am going to be plugging this information in to the third equation since I have two arbitrary numbers in my sequence. I'll say 16 is equals to 250 times r to the power of 5 minus 2. Now we could solve for r. So I might just do 16 divided by 250 first. Let's figure out what that is. I think I could do that in my head. 8 over 125 is equals to r to the power of 3. Take the cube root of both sides, and I get 2 over 5. And this time I am not going to say plus or minus since we are taking an odd root of this number. So we're good. No plus or minus here. If it was an even degree root that I was taking, like a square root or a fourth root or a sixth root, then yeah, I'll worry about the plus or minus. But this one, we're good. Don't worry about it. And so now I'll replug in r into the first equation using one of my arbitrary points as the arbitrary number in the sequence. I keep saying point. I mean to say number, but I think you guys know what I mean, right? Let's do u sub 5 here as my arbitrary one. We'll say 16 is equals to u sub 1 times r, which was 2/5 that we found a moment ago, to the power of, sorry, I just got a random text, to the power of 5 minus 1. And as long as I simplify and solve for u sub 1, we'll be good. So it seems like I'll have 16 is equals to u sub 1 times 2/5 to the power of 4. I'll take 16 and divide by 2/5 to the power of 4, and that's all equals to u sub 1. So let's plug that into the calculator. I have it already set up, which is nice. Let's delete the division sign and maybe do a fraction here. 2/5 to the power of 4. And I get u sub 1 is equals to 625. Now that I know the first number of my sequence, I can generalize it for all numbers of the sequence by saying u sub n is equals to u sub 1 times r, which was 2/5, to the power of n minus 1. So I've answered the problem. All right, let's continue to number 9. Let's go ahead and drag down the equations again in case we're still unfamiliar with them as we go along, just in case you need to reference them. Oops, didn't mean to take the box with me. Let's just drag it. I don't need it right there. All right, let's continue. So here I'm given 3 pieces of information. I'm given the first term, as well as my ratio, and then some arbitrary number in my sequence. I just don't know which number it is, right? So it seems like I have every single piece that lets me plug into the first equation. So that's pretty convenient. So I'll say 768 is equals to 3 times negative 2 to the power of n minus 1. And then here, I pretty much have everything in the equation, which now lets me solve for n. This one will be slightly tricky, but I'll be sure to explain to you how to figure it out. So first up for sure, let's take 768 and divide by 3. So let's see, 768 divided by 3, I get 256 is equals to negative 2 to the power of n minus 1. Now, if you want to pause the video and try to figure this out, feel free to do so. If not, let's keep going. So, ideally, I wish I could solve for n, and it's a really precarious situation, right? It's currently in the exponent. Now, I'm going to give you a fact here to recall, to maybe aid your thinking, that in the past, if we have bases with some exponent is all equals to some base that's the same base to another exponent, let's say 5 here, I can technically set those exponents equal to each other because the bases will cancel and go away. Right? So I got x minus 1 equals to 5. I would somehow like to apply this logic to the current situation I'm on. I wish that these both numbers right here were exactly the same so I can cancel out the bases. Well, technically, I could write it like that. 256 can be rewritten as 2 to the power of 8. Now you might be wondering, well, Mr. Bowie, they're still not the same. Well, let's just make them the same by logic, right? Technically, 256 is 2 to the power of 8, but 256 is also negative 2 to the power of 8, right? When you raise a negative number to an even power, then that negative cancels and goes away. So technically, this is a valid mathematical statement from one to the next. So with that being said, now that my bases are the same, I can set those exponents equals to each other and solve for n. So I get n is equals to 9. Let's see if that finishes out the problem. I think that's all that they asked me to do, I'm pretty sure. Identifying the value of n. Lovely, right? We finished the problem. Now let's do part B. I should probably box it in. Let me box it in first. All right, now let's do part B, where this problem may feel unfamiliar because they gave you 3 arbitrary numbers of my sequence, where I know 2 specific ones of my sequence, but I don't know the third one. I don't know which number of my sequence is this one, right? And so, based on just the previous problems that we did, the one directly above, whenever I'm provided 2 arbitrary numbers of the sequence, just like it was given here, what I did was use the third. All right, sorry for that awkward cut. My mic likes to cut out every now and then. All right, but we're good now. What was I saying? I think I was saying, yeah, so basically, whenever I was given 2 arbitrary numbers of sequence, I used a third equation to help me solve for r. So I'm pretty much going to repeat this key steps here to help us solve part B. Okay, so let's do that. So I'll take a sub 7, 64, is all equals to 486 times r to the power of 7 minus 2. Right, so we can solve for r now, just like I did in the problem above. And so I'll take both sides and divide by 486. So I get a really nasty decimal number, but I imagine if I press the fraction button here, I get 32 over 243, a nice fraction. All equals to r to the power of 5. And then I'll take the fifth root of this fraction, and I'll get 2 over 3 is equals to r. Now that I know what r is, I can re-plug this back into the first equation. So I'll say a sub n, some arbitrary one, but let's pick this one. We'll say 64 is equals to a sub 1 times 2/3 to the power of 7 minus 1. Now, of course, you can start plugging this in to figure out that n right now, but I kind of want to do all of the steps just in case they ask you for extra information. It's better off just to figure out it this way, okay? If you don't know what I mean, don't worry about it. Just continue to do the same steps we kind of did here, okay? So let's simplify now and solve for the first term of my sequence. I should have 64 is equals to a sub 1 times 2/3 to the power of 6. Let's divide both sides by 2/3 to the power of 6 now. So I have 64 divided by 2/3 to the power of 6, all equals to a sub 1. So let's plug that into the calculator. I get 64, 2 divided by 3 to the power of 6. So I get a sub 1 is equals to 729. And then now I'll replug this back into the first equation so I can solve for a sub n here, this arbitrary number of my sequence. So let's see where it belongs. So I'll say 324 now is equals to 729 times r, which is 2/3, to the power of n minus 1. Then we'll just simply simplify what I can and solve for n. So I'll take both sides and divide by 729. So I get 0.44 repeating. Let's go and change it to a fraction. I get 4/9 is equals to 2/3 to the n minus 1. And then technically 4/9 can be rewritten in such a way that it's the same as 2/3. Technically 4/9 is 2/3 to the power of 2. So we'll use the same trick as the previous problem. Now that my bases are the same, we can cancel them out and set the exponents equals to each other. Now solving for n, I get n is equals to 3. And that completes my problem. All right, we're almost done, don't worry. I know these video notes were pretty long so far. Now let's do number 10, and we'll leave number 11 alone, right? That one's kind of a toughie, but I'll give yourself the chance to do it yourself if you can figure it out. All right, number 10. The quantity of rabbit droppings in Miss Cautious' backyard doubles every week. 3 square feet is covered in droppings at the beginning of week 1. How much will be covered at the beginning of week 8? So let's think about the information that's given to us. I know in week 1, let's just say W sub 1, they had a total of 3 square feet of dropping. So I'll say W sub 1 is 3 feet squared. All right, let's include our units. And I'm wondering about, well, at week 8, how much will be covered at that week? And then I'm also given the R value based on this first sentence here. My ratio is equals to 2. Now I pretty much know every single piece of the first equation. So let's use it to solve for week 8. So W sub 8 is equals to 3 times R to the power of 8 minus 1. As long as I plug in the right hand side into the calculator, I should be able to figure out how much droppings are in their backyard. So 3 times 2 to the power of, what was it, 8 minus 1, so 7? So 384. Now it just kind of verbalizes how much, just answering it directly, saying, hey, 384 feet squared is how much droppings exist on week 8. Perfect. We're pretty much done today's notes. Number 11, we're going to skip, leaving it up to you. And then here's just kind of a generalization of what we've been talking about so far. You can skip this part completely, or just kind of continue and just listen to these last few statements that we're making, right? So we know that an arithmetic sequence is successive terms have a common difference or a constant rate of change. Notice that the equation that they provided is very much the exact same as what I kind of given to you earlier in our summary box, where the only difference is maybe perhaps this spot right here, where they put the variable d in front when we had it in the back. It does not really matter, up to you how you're comfortable with where putting it. Then a sub 0 is the exact same thing, right? It's your initial number of your sequence, although canonically it's pretty much known to be a sub 1, doesn't really matter. And then d is my difference. And then a sub k is some, I don't know how to spell arbitrary, so I'm just going to say it out loud. Some arbitrary number in my sequence, right? Any number in my sequence. And then here it says, and arithmetic sequences behave like linear functions, except they are not continuous. Increasing arithmetic sequences increase equally each step. Slope always stays the same. So what they're trying to get across is like, yes, it is pretty much like a linear function. However, when we think about sequences and when we count sequences like a sub 1, a sub 2, a sub 3, right? Each number in the subscript here is counting by whole numbers. There's no like a sub 1.5, right? You don't count like that. right? So that means I'm not going to be plugging in any numbers between 0 and 1, 1 and 2 at all. So when you graph this equation on the left-hand side, right, there's a y-intercept of 1 and then a slope of 3, you get something like this. Right, I can continue if I want to, but that's about as much as I can do. And you would not connect these dots at all, because again, this is an arithmetic sequence, not a linear function. It was not continuous. Continuous meaning I connect them at all with every single possible x value between 0 and 1 and 1 and 2 and so on and so forth, right? Same thing kind of applies down here when we mentioned earlier that yes, a geometric sequence is resembling something that's an exponential form. The same idea still applies. Here I have a point at 8, and then at 1 we have it at 4, then at 2 we have it at 2, and then so on and so forth, right? It kind of makes this exponential type of curve. Although I do not want to connect them, that would be an improper way to evaluate this geometric sequence. So just leave it as the point that's given. Then here the equations are pretty much the exact same as we kind of saw earlier when we wrote them down. Not much has really changed there. Alrighty, if you want to hear more about this, come talk to me in class. If not, we are done with the notes. Um, well, that's it. Hope you guys have a good day. You guys are the best, and I'll see you guys in the next video. Bye bye.